So if you think about how that light is hitting Earth, right, it's only hitting a part of the Earth, and as it hits the Earth, it's got to spread out around it kind of spherically there, right? So, the radius of the Earth is 6,400 kilometers approximately, and, only half of the Earth is exposed. And so if we estimate essentially what hits the Earth, right, we could approximate, essentially a sphere, right, with the light coming in and a circle of light coming in. And so that circle, right, is going to spread out over the sphere of the Earth here. So pi r squared, we're dealing with this area here. And so, if we were dealing with the whole this much power, that's essentially how much power is hitting the Earth. Now, what's interesting about this is without the atmosphere, the Earth's temperature would be about 18 degrees Celsius, which is far too cold. Negative 18, rather, which is far too cold. So we have the greenhouse gases that are needed to be able to keep the Earth's temperature where it needs to be. So let's take a look at this here. The solar constant is S. For Earth, it's about 1,400 watts per meter squared. So if we take, intensity's power over area, the solar constant would be power over area if we consider that. And so power equals the surface, or S, the constant, solar constant, times the area. And the albedo for Earth is low for water and forests, and so mostly absorption there. But it's very high for albedo. The albedo is high for snow, desert, and cloudy areas where the light bounces off. So the average albedo for the Earth is about 0.3. And so if we consider that, right, and we have pi r squared, which is the area, we can get, and we know the albedo of the Earth, right? So we can place that in there. 1 minus the albedo times the solar constant times pi r squared will give us the power. And so if we look at that, 0.3 in there, we get about 70% of the incident, rays. And so, 30% is reflected right out. So what we also have to consider here is, how is that power spread out? And so, we have the surface area of the Earth, 4 pi r squared. However, with the light coming in, we'll have to consider that. So dividing the surface area of this, we can get the intensity, the average intensity on the Earth. And so that'll cancel out there. And so we're dealing with about, the average intensity. And let's go ahead and calculate that, right? So we're getting about a fourth of it, right, as we work through that. So if we think of the Earth's energy balance, the Earth radiates out what it receives evenly, and we can find the average temperature of the Earth. And so, what it receives, it radiates out, and so the Earth, there's a balance there. This Earth is surrounded by space, 0 Kelvin, so we'll assume that the Earth is a perfect black body. And if this is what we have coming in, and this is what we have going out, we can divide by area to get this value. And so what's coming in should equal what's coming out there. So if we know that's true, if these are equal, we can find the average temperature of the Earth. And we'll subtract those out, and we get, the average there